Here's an example of a function. Notice the domain of this function is all real numbers. Moreover, I don't have a picture of this at all. And if I didn't know anything about this function and I want to determine where the function is increasing and where it's decreasing, I might be at this for a very long time. But we have the power of calculus behind us. So let's use the first derivative test to determine where this function might be increasing and where it might be decreasing. In particular, the intervals of increase and the intervals of decrease. So first of all, remember that I need to collect all of the critical values, and then sort of the second filter of those critical values is the first derivative test, right? So critical values, remember, those are where the derivative is either 0 or the derivative does not exist. So in both cases, I have to take the derivative. That's the good first step. So here's a function. It's a polynomial. I know how to take the derivative of all polynomials. In particular, if I'm looking for critical values, take the derivative. F prime of x, that's easy. It's going to be the derivative of each piece. So the 3 comes down, I get x squared, minus the 2 comes down, 5x, plus 6. Of course, the derivative of 1 is 0. So here's the derivative of this function. Again, notice right away, this function is continuous everywhere, which means that the derivative, since this is the derivative, right, the derivative exists everywhere. Therefore, one case is gone. I don't have to worry about where the derivative might not exist because it exists everywhere. All I've got to look for is where the derivative might be equal to 0, I should say. Okay? So I'm going to just take this function and set it equal to 0. Right? That'll help me determine what x values make this equal to 0. Right? So I need to solve this equation. F prime of x is equal to 0. Of course, that means that x squared minus 5x plus 6 is equal to 0. And notice this thing is a quadratic. It actually factors nicely. So we can factor this equal to 0. There's an x and there's an x. There's a 3 and a 2 here. In particular, I get a minus and a minus. So the two values where this function is equal to 0, that is the derivative of f is equal to 0, are going to be when x is 2 and x is 3. These are two values that are clearly in the domain of my function. All I've got to do now is determine whether or not these really are transition points. And I'm going to do that using the first derivative test. So now I've rewritten what we came up with a minute ago. The critical values are up here, and I've drawn a number line. What I'm going to do is partition the domain of the original function and then determine whether this function is increasing or decreasing on each one of these pieces of the domain, okay? The partitions of the domain. Recall that the domain of the original includes all real numbers. So the domain here is from negative infinity out to infinity. And what I'm going to do, again, is partition this around these critical values to determine what the function is doing in each one of these intervals. In particular, one interval, you can see here, is from negative infinity out to the value 2, right? That's this one. The other interval is from 2 to 3. And finally, the third interval is from 3 out to infinity. Notice that I'm not including the endpoints because, of course, the function is doing something critical there. Again, even though I have critical values, I'm not guaranteed these are really transition points. Okay, so I don't really know ahead of time whether or not the function is increasing or decreasing and where it's increasing and where it's decreasing. Now what I'm going to do is, again, use the first derivative test to determine whether or not these critical values really are transition points. So again, I need to test a couple of values in each one of these intervals. Remember again, one of the beauties of calculus, the power of calculus, tells us that in fact, when a function is increasing or decreasing on an entire interval, the derivative of that function will be positive or negative for any point in that interval. That means that I only need to check one point in each one of these intervals, which is very nice, right? I've reduced the problem of checking an infinite number of points down to really checking 3 points, okay? So I need to pick a point, a test point, in each one of these intervals. You want to choose points that are easy to work with. look, the easiest point in this interval is probably 0, right? Because I have to plug this into the derivative after all. So let this be 0. That's my test value. My test value over here, pick some value, again, that's in between. You know, in this case, we don't have a choice. We're going to have to choose a fraction. I'll just pick the point right in between, right? So probably 5/2. I'll let x be 5/2. That's an easy fraction to work with. And finally, I'll pick a number in this interval. And again, I'm going to choose the lowest integer value if possible. Looks like 4 is a good point. So x is equal to 4. And again, what I need to do is test each one of these values in the derivative, the first derivative, by taking these values, putting it in for x up here, and determining whether or not the derivative is positive or negative. Of course, if the derivative is positive, we know the function is increasing on that entire interval. If the derivative is negative, that means the function is decreasing on that entire interval. Okay? So let's go ahead and check. Well, look, the first one's pretty easy. F prime at 0 is, well, let x be 0. So I just get 6. But that's obviously positive. I don't care what the number is. I just know that it's positive. That's all I care for. So that means the derivative, I'll write it down here, the derivative of the function is positive here. And it's positive for this entire interval. How about this test value, 5/2? Well, I have to take this number and I have to plug it in here. Now you can see why we don't want ugly numbers. So f prime at 5/2 is, well, it's 5/2 squared minus 5 times 5/2 plus 6. And when I expand this out, I get something like 25/4 minus 25/2 plus 6. And if I turn everything in fourths, then I get something like 25 minus 50 plus 24/4. And you can see that this is actually going to be negative. Okay, so I get a negative value here. It doesn't matter exactly what the number is, just as long as we know it's negative. So I know the derivative here is negative. That means if I'm drawing the sign of the derivative on top of this number line, I see that the derivative is negative there. Okay, that means that, again, for every point in that interval, the function is decreasing. And finally, I've got to check this last interval. You've got to go ahead and check every interval because you're not quite sure whether or not the function's increasing, and then maybe it keeps increasing, right? So we still have to check. So let's go ahead and check this last test value of 4. So f prime at 4, plug it into my derivative function here for x. So this is equal to 4 squared, which is 16, minus 5 times 4 is 20, plus 6. Okay, you can see why whole numbers are easier to work with. And you can easily, hopefully, see here that we would get, when we actually compute all of this, you get 22 minus 20, so it's positive. That's all that really matters. So that means that, if I write on top the sign of the derivative, that means for every point in that interval, the derivative is positive. And automatically we can see that, in fact, the critical values 2 and 3 were indeed transition points. I'll draw down below what the function's doing. Okay, so here I've labeled f prime of x, and maybe down here I'll write f of x. And you can see clearly that the function is increasing for every point in the domain down here. Okay, it's increasing there. It's decreasing here because the derivative is negative. And it's increasing again over here because the derivative is positive. That means we automatically know the intervals of increase and decrease for this function without knowing the picture at all, knowing what the picture looks like, even if the domain is infinite. Okay, this is great. So you see the power of calculus. So finally, when all the smoke clears, the first derivative test was used to determine that, in fact, these critical values were transition points. That means that in the end, when all the smoke clears, we have that. So thus, the original f of x, right? We're using these tests, these derivatives, to determine the behavior of the original function. So we always go back to the original, right? That means that f of x is, we saw that it was increasing, okay, on 2 separate intervals. On the interval from minus infinity out to 2, and from 3 out to infinity. And I know the function's decreasing from 2 to 3, right? So it's And I'll say decreasing, okay, on the interval from 2 to 3. So now we have the behavior of this function over its entire domain just by using the power of calculus, without having to check every single point. And you can see here that this is going to be quite useful. In fact, it'll tell us that if we sort of saw the picture of this function, okay, even without anything further, we saw the function sort of increasing, it transitions here, it's decreasing, it transitions here, so it looks something like this, which means that the function has kind of a local maximum and a local minimum, right? So we can extract even more information out of this, maximum and minimum values, but at the very least, we certainly know where the function is increasing and where it's decreasing along its entire domain.